Welcome back to ECE 441A, 541A. As we said last time, we're actually starting to move quite rapidly now towards our second exam, and I won't see you that much before the second exam, and that's going to be clear, I hope, from the announcements, but I will see maybe some of you later this afternoon or evening. After my other class, there's a tech elective and AMP info session tonight in room 530 at 5:30. Hopefully I will be able to make it at that time. I may be a little bit late coming from my other class. Homework number 4 is due on Monday. Homework number 5 is due on Wednesday. Our exam, second exam, is a week from Friday. And a week from today, next Wednesday, I won't be here, so I will not have office hours or a class meeting on Wednesday. But stay tuned. I will try to give you material so that you don't feel left out, and in my absence, you can watch it before or after the normally scheduled class period, but there's probably going to be some additional material available to you, and all of that is to help you complete homework assignment 4 and 5. 5 obviously will be due on that day, and then we have our second exam a week from Friday, and there should be material for you to practice with on D2L relative to exam number 2. Another time that we will not see each other in this facility is a week after the exam. That's homecoming weekend, and engineers breakfast will be that morning, and we are encouraged to not have class formally at 8 and 9 during that day on the 26th of October. So you don't have to come here. You can go somewhere else, and again, stay tuned. There probably will be material available to you so that we can keep moving through the class, even in our absence, physical absence. Lab number 2 is due then the following Monday, the 29th of October, and hopefully you have your material now graded. That was returned to the team member that submitted or uploaded your lab onto D2L. I simply evaluated or pushed the evaluate button for that person, and some of you had multiple submissions. I maybe sort of randomly picked. Actually, I tried to find the most recent upload from that team and work from that. That material is available to you, hopefully, from sharing of your teammates' information. Today, what I want to do is provide you with some interpretations of these word problems for homework number 4 so that you don't spend as much time trying to figure out what's being asked and more time working the problems. That's what I want to do today for homework number 4, and then we will pick up with this another trade-off. Control is full of trade-offs, and this trade-off is settling time and steady state air. We'll look at some settling time examples for 3 typical plants, and then I will have a quiz for steady state air based on those plants, and then we'll start looking at some of those ideas together. But one thing that I might try to remember is that we will start looking at different system types today. And the system types will be classified as a type 0, a type 1, a type 2, and those are determined by what's in the forward path in our block diagram. The combination of our controller and plant, we'll put those together and say, is that combination type 0? Is it type 1? Is it type 2? And what do I mean by that? Well, the type depends on how many poles we have at the origin. So if you have a type 0 system being the controller-plant combination, then type 0 means you do not have any poles at the origin in that combination. A type 1 says you have one pole at the origin with this product of terms G sub C G. Type 2 is you have 2. And that will be important, or that plays a role in this steady state error computation when we have unity feedback in a negative way in our block diagram. Here are what I hope are hints for homework number 4. Paraphrasing the word problems, part A says determine the sensitivity of the system to changes in the engine gain. Well, what's the system? We have multiple inputs and we have one output. What's the system? So let me just tell you what the system is, or what I'm going to just assume the author is meaning by the system. Let's let that be T sub 1, the transfer function between the reference input R, which is the speed setting, and the actual speed of the vehicle. That's what I'm in part A labeling as the system. That's T sub 1, the transfer function between R and V. So part A, you need to find that system, and it will be parameterized by these different variables in the block diagram. But now you're asked to find the sensitivity of that transfer function T sub 1 with respect to changing this gain on our engine and vehicle, K sub E. That's part A of problem P 4.6. Then part B says determine the effect of the load torque on the speed. What do they mean by the effect? Well, the effect is actually a transfer function. Who knows? Well, now you do know. So now what they are calling the effect is a different transfer function. It's the transfer function between the load torque and the speed of the vehicle. And that's what I'm labeling T sub 2. So now we have two different transfer functions associated with this block diagram, which makes sense. We have two inputs and one output. And in the first one, in part A, the system was T sub 1. The effect is T sub 2. In part B, what you're asked to find the effect. Simply find that transfer function T sub 2 between the disturbance input delta T sub D and the speed of the vehicle V. And you know how to find these transfer functions. That's block diagram algebra, or that's Mason's gain. That's not really the challenge. The challenge on a lot of these problems is interpreting them. What do they really mean? Problem, or part C of this problem, says determine the constant percent grade. This is now, think of this as you're going up a hill. This is a cruise control problem. And now it's asking, what's the slope that will cause your vehicle to stall? So that slope is now the disturbance coming in, messing you up, and they actually give you some additional information. They tell you that you're going along at 30. I don't remember the units. That might be kilometers per hour. It might be feet per... I don't remember the units, but it's 30 as your reference speed. So now you have speed determined by two different components, the reference input and the disturbance input. If you're stalling, you want that resulting speed, V of S, to be 0. And you're given what R of S is. That's 30 over S. Now what they're asking you to find is this number, delta D. How big is that slope that you now are seeing as a disturbance on your cruise control? How big is that slope to cause your vehicle to stall? And all of this would be in steady state, meaning now you're assuming that you're rolling along and you come upon this grade. What's the grade that would cause you to stall? Is that clear? That's one of the problems in homework number 4 with multiple parts. Another problem. Again, they're using the systems and effects, etc. in their descriptions. This says part A, what is the effect of t sub d on y of s? Again, the effect is that transfer function between the load disturbance, t sub d, and don't ask me why in one problem they use delta t sub d to mean the input, and this one they just use t sub d. It's basically the disturbance input in both cases. Don't read any more into that, okay? One has a delta, one does not. Big deal. Don't worry about that difference in labeling. That's all it is a label. So in part A, the effect is simply find the transfer function. Then, in the second part, they say determine the sensitivity of the closed loop to k sub 2. Well, this system's in a closed loop under multiple inputs. What's sensitivity? Well, let's just assume the closed loop now means the transfer function from the earlier problem. It's the transfer function between the desired joint angle and the actual joint angle. This, let's say, is some robot or machine that you're wanting a desired angle and you have an actual angle. Now, to find the sensitivity of the closed loop to k sub 2, the sensitivity will be with respect to that transfer function t sub 1. And you'll find that sensitivity relative to parameter k sub 2 in your system. That's part B. Did this have 3 parts as well? And then they ask, what is the steady state error when the desired joint angle is a unit step, basically, and the disturbance is not active? But now you have to pay attention, because look at this block diagram. What's in the feedback path? Is it unity? Is the feedback path unity? Is it 1? No. It has an S term unless k sub 4 is 0 and k sub 3 is 1. So when they ask about the error, now you need to define the error, which is not anywhere explicitly in the block diagram, to be the difference between your desired joint angle and the actual joint angle. So you now have to put this into an expression yourself. It's not going to be a signal in the block diagram. And you can use the final value theorem once you have y of s, which you have now by finding t sub 1 in part B. And t sub d, the second component that could be impacting that actual angle, the disturbance, has been set to 0. So with zero disturbance, what is your steady state error? The next problem is also a steady state error problem. And what the signal is that you're applying, this is now a welding problem, and now you have a jagged set of parts that you're welding, let's say. And you're now trying to follow this sawtooth waveform. This is where you want your weld to be. That's shown now in whatever color this is. Is that green, sort of? You guys tell me. My eyes aren't working this morning. Is it blue? Blue-green? Teal? Okay. Let's get out our 124 crayons and start comparing those colors to this But whatever it is, that's where you want to be. That's your desired. So how do you get a steady state if you're always going up and down, up and down, up and down? What does it mean to be steady state? What's a steady state error when we have something that just it slopes up, then it slopes down, it slopes up, slopes down? What do they mean if they want to know my steady state error in this welding problem, where you maybe are given a G of S, the plant, a controller, G sub C, and now you want to follow this R of T that goes up to 10 in 10 seconds, it goes down to 0 in another 10 seconds, etc. What is going on? Well, if you now applied this reference to that system, what will it do? Well, it might actually do something like this. It might sort of go there, and now you change direction on it, and it has a little bit more of a change. Well, I'll show you the picture in a minute, but what you're wanting to do is really just assume that that goes on forever, and that now your steady state error is that distance between where you want to go. If you were continuing to go up at a slope, what's the slope on that teal line? 1. Now if you're not quite at 1 on your slope, there's a difference. There's an error between where you are, which is red, and where you want to be, which is teal. That's the steady state error. And you can see that there might be a slight transient when you first start. But we're playing on the fact of infinity. What is infinity? Well, when we think of infinity, a lot of times we think, oh, we'll never get there. But in this class, what do we think of when we think of infinity? 5 time constants. That's not very long in some cases, is it? So in this particular scenario, hopefully we have reached our 5 time constants before we hit 10 seconds. So that we're in a steady state pattern. And now you can identify the error in that region or in that time interval. Is that clear? If it's not, maybe you can now look at this diagram. Maybe this one is a little bit better. This is now figure 37 in chapter 5. Where you have the input, which is now shown dashed, and you have the actual output, which is solid, and the error, steady state error, E sub SS, is identified after you've now reached a steady pattern for your output waveform. And if that doesn't make sense, then you even have code that you can follow. So if you're in the half that like to see code, this is the code, the MATLAB code, that produces this figure to try to determine what is my steady state error. Questions on the hints for homework number 4? Or what you're being asked. So when they ask you to find the steady state error, hopefully now you say, well, I just keep moving back and forth, going up, then I'm down, up, down. Well, we're not doing push-ups or up-downs or something. We're actually trying to track this trajectory, and we do reach a steady state, hopefully, before we turn or adjust our reference input. That's the idea with that problem or set of problems. Let's now go back to our discussion of settling time, 2% settling time. We have our plant, G of S, and it's configured in a negative unity output configuration We may change that g of s. It might be different depending on the circumstance. We're going to look at 3 different cases, and we want to find the settling time for 3 different systems. And we're assuming that the reference input is the same for all 3 systems. It's just a unit step. Here are the 3 systems, and I tried to color code those. So we have blue, green, and black. A, B, and C. A we talked about last time in terms of parameter values of tau 0 of 1. What's tau 0? What's the word that we use to describe tau sub 0? Time constant. So we have a time constant of 1 in case A. We have a gain or a numerator, k sub 0 of 10. What's the DC gain of plant g of s in part A, or in system A? What's the DC gain of the open loop plant g of s? It's 10. That's k sub 0. Part B, we're changing the gain, or in system B, we're going to change the gain, lower it by a factor of 10, and we're going to change the time constant. Going to reduce it to a 10th from 1. If my time constant is 0.1 in the open loop versus 1 in the part A, which system is faster in the open loop, A or B? Based on time constant. Or if you don't think in terms of time constants, think in terms of poles. Where are your open loop poles? And which pole would be faster? Remember what we talked about last time. Now we're looking at this vertical line. How far into the left half plane? If we're further into the left half plane, our system is faster. In part C, we have another system, and this one's structure is now different. We now have a pole at the origin. This is now a type 1 system. The other systems, A and B, were type 0. We had no poles at the origin in system A and system B in the open loop. System C, we have 1 pole at the origin and 1 pole at -1. So now we put g of s into this closed loop configuration. We use cheer 2, g over 1 plus g, since h is 1, and we can now derive the closed loop transfer function in parts A and B because they have the same structure. We'll go ahead and derive part C when we get there. But we might as well derive the closed loop transfer function for plants A and B together, since they have the same structure, just different values or different parameters. And we're doing our when is 1. I don't know, I have this Sesame Street thing. When is 1 like the other? But here we have, I'm now saying the number 1, we're rewriting as a ratio of tau 0s plus 1 over tau 0s plus 1. That cleans up our denominators in both the numerator and denominator, leaving us with our closed loop transfer function, k sub 0 over tau sub 0s plus 1 plus k sub 0. Let's now look at what that does to our settling time. And this, I think, you've seen in the AC notes from last time. From before, part A, time constant of 1, gain of 10. We plug those values in and we end up looking for our dominant closed loop poles. Do you remember what I'm trying to refer to when I say dominant? Closest to the origin. If I had 6 poles, now you would be looking at the pole closest to the origin, or poles if you had complex conjugate poles. You would be focused on those. Those are now dominating your response. Those are the slowest. Those take the longest to get to where they're going. Those are the poles at near the origin. Those dominate your response. In this case, with a gain of 10, a time constant of 1, we end up with a pole at minus 11. Our sigma then is 11. Settling time, T sub s, is 4 tau for a 2% settling time. Tau and sigma are reciprocally related. We have 4 over sigma. Sigma was 11. Our settling time in plant A is 0.36. 0.363636. About 0.4 seconds for our settling time. So in less than half a second in the closed loop, this first system has settled. That's infinity. In 0.4 seconds. Question? Why do I have sigma is equal to 11? Anyone want to help? Is that the question? Where did sigma come from? Where did sigma come from when maybe always before we were using it when we were having complex poles? Maybe that's the confusion. Whoops, now I'm in red. I'm not sure you like that. But before we had, this was our sigma, and this was omega sub d. Right? The real part was sigma, the imaginary part was omega sub d. Now I just have one pole, and this is now my sigma. The distance that pole is into the left half plane, S-plane, is my sigma. Did that? In this case, I'm saying, where's my pole? I only have one pole. I'm looking for it. Here, boy. It's at minus 11, so it's 11 into the complex plane. That's my sigma. And now the bigger the sigma, the farther you out are into the left half plane, the faster your response. That's part A, and that was from before. Let's now look at what we have in part B. Part B, we have exactly the same structure of our plant. This is what's the system type for this G? Trying to train us on new words, new terms for today, because you're going to be using those for exam number 2. What's the system type for G? 0. We have no poles at the origin in this plant, G. There's no pole at the origin. That's a type 0 system. We do have a time constant of 1/10 of a second, and we have a gain of 1. And now we can find our closed loop transfer function for this particular set of parameters, and that's going to now be 1 over 0.1s plus 1 plus 1. Or now where is my pole? I set my denominator equal to 0. I solve for all the s's that cause that to be true. In this case, I only have one such value. And I end up with a pole at minus 20. How many closed loop poles do I have for this case? 1. What's my sigma? That's how far I am with this one pole away from the origin. That's 20. Is that clear? So my sigma for a one pole is just that pole location. My sigma for a complex conjugate set is their real part, or their real component. Now what's my settling time for this system? It hasn't changed in formula. It's 4 tau, which is 4 over sigma, 4 over 20. It's 1/5 or 0.2 seconds. So this system, what was its DC gain? What was the DC gain of this system? Open loop. What's the DC gain of this system? One-half. Our A was 10. But now what do we have? We have a faster system. Before it was roughly 0.4, now it's at 0.2 for our settling time. Our system is faster for this combination of time constant and gain. Let's now look at the third system. G of S here was structurally different. And we want to now find the settling time for this system. But before we do that, let me again try to drive home this new term that we're using. What's the system type for this G of S? This is a type 1 system. So this is a type 1 because we have one pole at the origin. This system type is going to be important when we start talking about steady state air. What's the closed loop system? Cheer 2 hasn't changed, and this is now the transfer function between the output over the input. We now have 1 over S, S plus 1 over 1 plus 1 over S, S plus 1. And we can do our conversion of 1 again to S over S plus, S times S plus 1 over S times S plus 1, and we're left with 1 S, S plus 1 plus 1. Or now, we do have 2 poles. We had 2 poles in our system, didn't we, to start with, G. Now we closed the loop on that, and now our closed loop transfer function, if we wanted to look at the poles, where are they at? If you factored this by completing the square, do you see that S squared plus S could be created by looking at S plus 1/2 quantity squared? Now we have S squared plus 2 times 1/2 S plus 1/4. And what do we need to add to 1/4 to get to 1? 3/4. So now we are doing the square root of 3 over 2 squared. That's now our another way of writing the denominator, S squared plus S plus 1, is S plus 1/2 squared plus square root of 3 over 2 squared. Why? Well, now we know exactly where that pair of complex conjugate poles are at. They now have a real part of minus 1/2 and an imaginary part of square root of 3 over 2. Ooh, that's an ugly imaginary component. Let me clean that up a little bit, maybe. So that's about 0.8 something, isn't it? Square root of 3, 1.7 divided by 2. So we're a little bit more in imaginary component than real component. But that's where our closed loop poles are in this case. Does that help us in any way with our settling time? I'm not changing the formula, but now I have to change my sigma. What's my sigma? This has a settling time of 8 seconds. So A had a settling time of 0.4, B 0.2, and C 8. Now what we want to do is, well, before we move on, that now is our discussion. Hopefully you understand how to play, how to compute, how to find settling time for a given pole or system, G, and it connected in a closed loop manner. Which system, now we're switching gears a little bit, blue, green, or black, which A, B, or C, which system has the best steady state air, air steady state, and the worst steady state air? We haven't talked about this yet, but that's where we're going, but I'm trying to get your intuition thinking, or your mind thinking about steady state air. We've been talking about settling time, and there are the settling times for the 3 different systems: 0.36, 0.2, and 8. Now, how many ways can we look at best and worst? Well, we have 6 combinations. Is System A the best and B the worst? Is A the best and C the worst? I need you to vote. So now you are going to maybe have to lay down a pencil. You don't need to take off your shoes for this one. This one is just 6, but I want to see, well, I guess show of hands when I just ask for, no, let me, hate for people to influence each other. So we will vote all at once with a show of fingers, show of digits, but then after that I will say you can't change, you can't go back and backspace and change which fingers you had up. But now tell me, did you hold up for 1, for 2? Does that make sense? So now at the count of 3, I want you to tell me with your hands whether you're voting for 1, that pair, A is the best, B is the worst, or 3, B is the best, A is the worst, etc. Do you see what I'm asking? Which combination gives you the best steady state air and the worst steady state air? Which combination of systems? A, B, or C paired up? 1 through 6. The count of 3, I want to see fingers. Okay? 1, 2, 3. All right, so don't change your vote and tell me when you held up your, or how many digits you had held up. How many were holding up 1 finger? Now show me a big hand if you were doing 1. No one voted for 1. 2. 3 votes. 3. How about 4? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I apologize if you're playing along at home. I can't count you, but I can see that you've raised your hands for some of these. 5. 1, 2, 3. 3. 6. 1, 2, 3, 4, 5, 6, 7, 8. Why do I feel like I'm not counting? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, well, let's see if we can figure out what the best answer is on this next round. I'm afraid we maybe didn't answer the correct way. That's okay. This wasn't an exam. This was a question. But do we remember what steady state error really means? Here's one case that might bring it home jarringly. I went into the lab last night and I actually started trying to simulate with spring number 4. What a an ornery system, I should say, right? So I got all sorts of answers, but here's one of those. I used a case of PF of 0.1 to kick it a little bit harder. The spring is so weak and the friction is so big that you might kick it and then it just goes, oh, I'm going to stop. I'm not going to pull it back. My restoring force isn't that strong. The friction's overwhelming. So in some cases, you don't even hardly get any overshoot with spring number 4. You just go up and stop. And then the other half, when you now come back, that's sort of like an initial condition response. So now at seconds, what the heck? Oh boy, forget the x-axis. This was late at night when I was doing this, so that's at 3 seconds, is it not? So I think, oh, my time, you can check that's the number of samples. So time is data. I think that's supposed to be column 2, and I use column 1. So forget the labeling on the x-axis, but you get the idea. You know what you did, right? You held it for, what was the dwell time? Was it 3 seconds? And then you let it relax. Well, the relaxing part is like an initial condition response. And that one actually kind of shakes like, but it's still not very linear in behavior. You would think it would bounce back up and then it would come below and go back and then it would die out. But the friction is so big relative to this soft spring that the spring goes, I'm done. And it doesn't last very long. In this case, what's our steady state error? That's what we're focusing on today. Do you see that we've reached infinity? I guess maybe that's what I was thinking on my time, but that's not the right labeling on time. Infinity doesn't take very long to reach. And we reach it 3 different times in this situation for the excitation. We command it to go to 2000. That's correct. That's position. And do we get there at infinity? In this case, not quite. We don't quite get there, but our steady state error can be measured right there between where we wanted to go, our reference of 2000, and where we actually made it, which was maybe about 1800 counts or something. And that steady state error might not be the consistent for each of these cases, but it's pretty close. That's the steady state error for the lab. That's what we're talking about when I say, what's the steady state error? And here's another one. Here's a sawtooth tracking. This is similar to figure 37 in chapter 5, but here is my own. Who knows if it's even close to being valid, but I'm going between 0 and 2 in vertical displacement, and then I go from 2 to -2 over a given length of time. The red is the reference, the blue is the output. Do you see that when I change directions, I do have a transient? I don't lock on and stay with the same distance away when I start redirecting my robot. If I say you're going up at a particular slope, now you're going down at a slope. Well, when I change directions, I experience some transient. But do you see that you can identify some steady state error there? in this case, where would you draw or measure the steady state error? But it's not flat, it's not constant, I don't know, it's sloping. What's my steady state error? I give up. Do you see how you can find the steady state error? I'm trying to go up at a particular slope, and I'm following that slope, but there's a mismatch. I'm not locked on. I'm not on top of where I want to be. So my steady state error, again, could be measured somewhere before you reach the turnaround or the change in command location. Now, to get that measurement of a steady state error, we're actually making some assumptions. Now, and here are some commands that I know that a lot of you want to see code, so you'll have this in the notes. Okay, there's some code. But what are we assuming in arriving at this steady state error? Are we making any kind of assumptions in order to measure or give your boss a value? If he says, what's the steady state error in this robot's tracking behavior? What are we assuming? What would happen if it went sort of like this, and then you change directions? What are we assuming? The system settles. The system is actually stable, isn't it? The system is actually stable, so that's one of our main assumptions. The closed loop system is stable. And we would need to verify that, but actually last night I actually verified it. That's where the poles are, the closed loop poles for this particular system that I simulated. These are the closed loop poles, and you can check the code. I know you're going to want to do that. So you would need to verify that before you even start talking about a steady state error. If I say, what's the steady state error? And you go, my system's not stable. Well, then we can't even talk about steady state error. Is that clear? You don't have a steady state error if your system's not even stable. So now we would check the root, or check the closed loop poles. And again, you can check the code to see how you might do that. And that's the roots of the closed loop denominator polynomial. What else are we assuming? What are we assuming here, or maybe it's cleaner or easier to see here? What are we assuming when we talk about a steady state error? Okay, we've settled. Whoops. We're stable, but what else are we assuming? Did we just keep going like this? Oh, and then we switched, and then we switched. We actually settled, didn't we? We reached a steady state. The transients are gone when we started talking about steady state. So another assumption is we are assuming that the transients are gone before the signal changes again. One more assumption that we're making. we're treating the first time segment, if that's where we do our steady state error, as if it goes on forever. We're using the final value theorem if you're doing this analytically. We're just assuming that eventually, even though we switched, if this was our command and we actually were doing something like this, we're just assuming that all of this goes on forever. We'll pick up at that point next time. We're way out of time. Thank you for staying with me.